Hello everyone, and welcome to this next video lecture. Today we're going to continue to talk about the difference of two means, doing inference on the difference of two means for non-paired data. So I believe what we did at the end of class, frankly I hope we got to it at the end of class, is we developed these two hypotheses. The population average of babies' weights for women who smoke, which smoke is just going to be SM here, minus that same thing for non-smoke, right, is equal to 0 versus the alternative hypothesis that this difference is not equal to 0. And I think I chose an alpha of 0.05. Okay? And we did our first step already where we determined in step 1, we determined that X bar smoke minus X bar non-smoke is normally distributed. Or at least we established that it is, as long as we can establish that both of these individually satisfy the conditions for normal distribution. So if we get that each of these X bars are normally distributed, then their difference is going to be as well, and we can do inference just like we've been doing for the last, I guess, week and a half now. Maybe it hasn't actually been that long. I think we relatively learned how to do these hypothesis testing stuff. Anyway, so we have these hypotheses. We talked about step 1. Now I want to talk about step 2. Excuse me. Step 1 is technically just making these hypotheses. So maybe I should say that this is step 1 right here. Step 2 is the easiest step. It's what we always do. We assume that this is true. Assume the null hypothesis. Then we can do step 3, which is calculate the p-value. So let's do what I just said. Let's confirm that X bar smoke and X bar non-smoke are normally distributed. So I think we already have that they came from a simple random sample, so that checks out. And the simple random sample represents less than or equal to 10% of the total population. Let's start with, this is non-smoke. So this is a distribution. I am seeing a left skew, which is a little troubling, but let's go ahead and look at what their sample size is as well. So this is X bar non-smoke was 7.18. Looks like the standard deviation of this is 1.6, and the sample size is 100. So I would say that there's definitely a left skew here, but a sample size of 100 is large enough for us to still apply the central limit theorem, and by the central limit theorem, this second one, X non-smoke, is normal. So we've done this for non-smoke. Let's now do it for smoke. Okay, so these are the weights of newborn children for mothers who do smoke. And I want to say X bar smoke is 6.78. Standard deviation is 1.43. And smoke is 50. So again, I think we have a big enough sample size. This one seems a little bit less left skewed, but still definitely left skewed. But I would say we still have a big enough sample size to apply the central limit theorem. 50 does certainly represent less than or equal to 10% of the total population of infants whose mothers smoke. And this sample was done via a simple random sample. So we have large enough sample size, we have, if there is a skew, we have enough of a sample to make up for it, and we have the whole independence assumption. With all these things, we can also assume that X bar smoke is also normal, and thus X bar smoke minus X bar non-smoke is normally distributed. Cool. Well, what do we do next? We need our point estimate. Well, the point estimate's not that hard. It's literally just what we calculated from our sample. But it's 6.78 minus 7.18, which is equal to, I really should just be able to do this math, but I never really trust myself. I think it's 0.4. Okay. We need to know the standard error, so we need to know X, the sigma of X bar smoke minus X bar non-smoke. And this was something I actually gave you a formula for in class, and it's this thing. The standard deviation of all mothers who smoke over the number of people that we sampled from the smoking group plus the population standard deviation of people who of infant weights from mothers who don't smoke versus over the number of people we took from that population. So this is non-smoke. Okay. And since we don't actually know the population standard deviations, we approximate them with the sample. So this is, oh, and all of these should be squared, excuse me. Because we're actually using the variance here. Cool. And this is just going to be equal to, using our numbers, what, it was like 1.6 squared over 100 plus 1.43 squared over 50, right? Which is around 0.26. Cool. That's that. Thus, X bar smoke minus X bar non-smoke is distributed normally with this distribution. So it looks, the difference of the means is going to look something like, have a distribution that looks something like this. It is centered at the true population difference, which we assume by the null hypothesis was equal to 0. And I think about right here, we have our observed difference of the sample means. Okay? So, since we have this, we calculated this as our, well, we did it way back here, as our difference between X bar smoking versus X bar non-smoking. We are interested in knowing the probability of being at or below this value. And once we find this number, we'll just times it by 2 to get our p-value, which is kind of cool. So how do we do that? We calculate the z-score, right? Z equals x minus mu over sigma. It's going to be negative 0.4 minus 0 over, what was it, 0.26? Which is around negative 1.54. And we can plug that into our norm.s.dist function. That's going to be equal to 0.062. And since we're working with a two-sided hypothesis test here, we need to times this value by 2. And note, step 4, we make our decision. So alpha was 0.05, and this is less than 0.124. And when we have this, we fail to reject. Okay? So that is how this works. This is how you would do a hypothesis test for the difference of two means for data that is not paired. So just like how we can do hypothesis testing and therefore inference, we can also make a confidence interval. So the general framework for confidence intervals applies for both cases. Paired data and non-paired data. And it's the same formula. You take your point estimate, you add or subtract a critical value times your standard error. So let's use the book prices example, which I think we went through this in lecture. It was this was the paired data example. I'm sorry, I don't have it right here, but go back to the lecture, it's the paired data example where we had the book prices from UCLA and the book prices from Amazon, and we were trying to look at the average differences between these paired data points. So I'm just gonna write that. So for our book example, book prices example, a 95% confidence interval is done with these things. So for that example, our point estimate was the average of the differences, right? We took all of the differences and we averaged them up and got this value. And I think in that example, it was 12.76. Similarly, the standard error was just the standard error of the mean differences, which we approximated with the sample standard deviation of the mean differences, right? Which was around 1.67. And then our critical value was actually the same thing it always is. Z of alpha over 2, the absolute value of C of alpha over 2, which here is around 1.9599. Okay? And if you put these all together, literally just plug them into our usual formula for the confidence interval. If you plug these all together, you'll get which I believe, if we were to try to do the hypothesis test we did for the books, again, look back in the previous lecture, this corresponds to a rejection of that hypothesis test, which corresponded to when we actually did the hypothesis test. We rejected, and it looks like, as always, our confidence interval aligns with what we said in the hypothesis test. So, what was the big idea here? We used the same formula for confidence interval. We got these three values, which we calculated in our last lecture, and we just put them together to make the confidence interval. And this has the same interpretation as always. Confidence intervals, approximately 95% of confidence intervals made in this way will contain the true population mean difference. So this X bar differences corresponds to some true value if we knew every single data point, and that true value we are 95% confident belongs in this interval. Okay? So that was paired data. Let me real quick do the same thing for the non-paired data. So this is for mothers smoking example. We wanted to look at the weights of infants for mothers who smoke versus the weights of infants who mothers who don't smoke. And recall, we failed to reject this hypothesis, right? We wanted to know whether or not there was no difference. And again, I'll do a 95% confidence interval. That seems the number that we usually use in classes like this. And just like before, I need to know my point estimate to be able to plug into my formula. And here it was actually just X bar smoke minus X bar non-smoke, which we calculated to be negative 0.4. Our standard error, this was this was more complicated. It was the standard error of X bar smoke minus X bar non-smoke, which was that crazy formula we did up here, right? It was this thing. So it was what, 0.26? So this is 0.26 or around that. This is an approximation. And our C-value remains unchanged. We had normality, so we use a normal critical value. That's what this is called. We take the absolute value of the alpha over 2th percentile of the Z distribution, and this, just like before, is around here. So again, we just plug all these things in, and we get this. And note that since 0 is in this interval, we fail to reject. 0 is our null value for this one. We fail to reject the null hypothesis. Okay, so up until now, we have now learned inference for paired data and non-paired data, and we have learned how to make confidence intervals for the true population difference and the true population difference of means. So you didn't quite understand that sentence that I just made. You should go back to these lectures and understand what's new here. It's sort of, we're applying things we have really already learned, but we're doing them in a new context. And there's some little new things that change, but it's mostly just applying the things that we've already done. And it's definitely in the same framework, right? This right here with the arrows is the framework of a hypothesis, of a confidence interval. We always have a point estimate, and we plus or minus critical value times the standard error. And these 4 steps that I went through to do this hypothesis test are the same 4 steps we had always done. So same framework, a little bit new way of looking at it. All right, that is it for today. Thank you so much, everyone.